Welcome everyone. I will start this session with an introduction to causal model evaluation and some first results in the context of the EERIE project. So first of all, the brief outline. So I will try to give you an overview of the motivation and procedure of causal discovery, and then what this can be, or how this can be used for causal model evaluation, and then go over to some first results, and in the end give you a brief summary and an outlook what we want to further do in this direction in EERIE. So first of all, why do we do causal discovery? So as you might know, correlation does not always mean causation, and you can find, when you do a simple correlation analysis, some spurious connections due to several factors. So for example, you could have autocorrelation of the variables you're looking at, or let's say you want to analyze the connection between, or the relationship between X and Y, and you don't know, for example, that there also is in Z, then you can have different problems like confounding, where Z influences both variables X and Y, and so you would find a correlation here, or this colliding here, where you would find, if you would also look at the relationship between X and Z, would find a spurious connection here, or you would have a mediation here. So there's not always a clear causality if you do a simple correlation. This is also shown in the example in one paper where one of these causal discovery algorithms was published. So here in Runge and others from 2019, they show that if you do a time-lagged correlation analysis between the Nino index and the temperature of British Columbia, you would find this gray link here, which is a spurious link, because the temperature of British Columbia does not actually influence the Nino index, which is relatively well known. And so when you do this causal discovery here, you only find this time-lagged link. So this is the 2 is for time lag, but I will show you that also later how these graphs look. And so causal model evaluation comes in here, that we can look at actual causal pathways between the variables we want to look at, and then assess from let's say observations or reanalysis how well the Earth system models are able to reproduce these graphs. And then we can also look at what changing things in the model or in the grid does to this analysis. So how is causal discovery done? So yeah, just very briefly. So you have, for example, here these 1, 2, 3s are your, let's say, observational or model data sets, or on some area. Then you can run it through ESM Valtool or your own pre-processing script. So what you need in the end is then you need time series that abide by some assumptions. So for example, one of the big ones is stationarity, which means that if you have a seasonal cycle, you need to remove that and have monthly anomalies, for example. And then you would do like an area mean or something. So you have these time series. And then you can run it through this algorithm, for example, PCMCI. So there are several causal discovery algorithms bundled in this TIRAMAT package. PCMCI Plus, for example, was presented in this paper here by Runge in 2020. And then this algorithm gives you such a causal graph where you have different types of links. So for example, you have these band links, which are lagged links. So this one, for example, it would mean a time lag of, if it's monthly data, 1 month. Then you have contemporaneous links, which are straight, and you have different colors. So for example, reddish links we indicate a positive relation, bluish links a negative relation, and then you can also have links like with this dot that are undirected. And if you are very unlucky, you can also have x's here, which with which the algorithm tells you that something is wrong in your some assumptions are violated, but won't go into detail here. So if you do this for different data sources, so for example, observations and different models, you can get your different graphs here. And just beyond inspection by eye, you can also calculate, for example, F-scores, which are a similarity, which is a similarity of, a measure of similarity. And then you can, for example, in this paper by Novak and others in 2020, look at this similarity matrix. So look at how similar different models are to each other. So here are several CMIP models, or you can look at these models compared to reanalysis and look at, okay, how well do some, or how well can these models reproduce this graph from the observation. And one example was recently done by a master's student in our group who graduated here. He looked at precipitation patterns and the drivers over southeastern Africa. So here you have, for example, sea surface temperatures, then precipitation over certain areas, then some teleconnection indices like Nino, Indian Ocean dipoles, an annular mode, and some pressure patterns like the Botswana high, and zonal and meridional wind here, or average over these areas that are shown. And then, also only monthly anomalies for the austral summer, because we wanted to look at summer precipitation. And then you can get, depending, so yeah, as I said, there is this package, Tigramite, and there are several algorithms, but these algorithms are fairly complex, and you have some choices to do the analysis different, and then you will also get different graphs. So this is just one example of what he did, but basically, so if we look at this precipitation here in this area, you can see that, for example, the Nino index has a negative impact here, then the Botswana high as well, and the precipitation, the sea surface temperature here has a positive influence on this precipitation here, which are also, make sense, and also found like this in the literature. And one other thing he did is also calculating these F-scores. So you see that the reanalysis, the two different reanalysis sets he used, ERA5 and NSEP-ENCA, are the most similar data sets. And one interesting observation here is that if you look at these different models, so I think those were from high-res MIP, that if you look at different resolutions, there's one model where when you increase to HR, so a high resolution, you have a higher F-score, but for other models, for example, you have ECMWF here, low and high resolution, you have a lower F-score for the higher resolution, which is one interesting observation from his work. And then one example that we started working on for the Southern Ocean is looking at different variables averaged over this red bed here from the ORAS-5 reanalysis and from ERA interim. And it's, as I said, it's fairly simple, and we will expand on this in the future. But what you can see basically is that these links are sensible, and you can, so to say, see that the algorithm, at least for this, what we did here, does nothing unexpected, and so we can try to build on this. So we used zonal wind stress then the standard deviation of the sea surface height, sea surface temperature, salinity, and the net downward heat flux, just to get a, yeah, so that's that simple first overview, and this looks fine. So what we now want to do is, first of all, summarizing that the precipitation drivers for Southeastern Africa can be identified by causal discovery, which was shown by Jonas in his master thesis, and that we can get a fairly sensible first causal graph for the Southern Ocean air sea interactions. And now what we want to do is we want to refine this analysis of the Southern Ocean with more variables, splitting the heat flux, for example, looking at more mesoscale ocean variables, and maybe also analyze regional differences, which was also started. But yeah, that's something that we will continue in the future, and then finally apply this all to the EERIE models and look at what nice graphs they give us. And that's it from my side. Thank you.
Thanks, Jan. Are there any questions for Jan? I think Hannah has a question.
Great. Oh, thank you. Thank you for a really interesting talk. With the work from the master's student, did you then go in and try and work out, because it was a very summary statistic somehow with looking at the impact of resolution on this F score, did you then try and work out, you know, which of the processes were improved or not improved in the different resolution runs? Can you say a bit more about it, maybe? Oh, you're muted, I think, maybe, if you're, sorry.
Yeah, sorry. So what I wanted to say is that during the final phase of his master's thesis, I actually was on parental leave, so I might not have the full insight of what he did, but maybe Katja can add to this. But I think that he did not really go into the detail of the processes in these different resolutions. But yeah, as I said, maybe Katja knows more.
I also don't know the exact detail. He looked at all the graphs, but yeah, it was not conclusive. So some models did better, but there are also like only 3 models from the high-res MIP. Some did better in high resolutions, others not. But yeah, I know that he looked at all these graphs, but you see that they are rather complex, and Jonas concentrated kind of on what acts on precipitation, but this F1 score actually reflects the whole graph. And I think that he didn't go into detail, or he didn't analyze in detail. He just then looked on the similarity of the graphs, not in any, or not at every link in detail.
Yeah, I can see they're very, very overwhelmingly rich in terms of information, and so there's a lot to dig into. But yeah, thank you.
Yeah, and that's also already a reduced graph, so that where he looked, where he really put a lot of kind of work in was the 2 methods he used. One is this bootstrapping, and the other one I think that's shown here is the FDR false detection rate control that reduced the number of links. Else you get, with this number of variables, you get really networks where it's hard to find your way through. And yeah, on the other hand, it's always really difficult to fulfill all these requirements that this causal graphs need. So quite often it is not every driver in there, and then you can get spurious links. So it's yeah, not easy to analyze these things. And in the framework of a master thesis, I think he did a lot of work. But yeah, we're planning to follow on that a little bit. But yeah, that's not analyzed in that detail. Are there more questions? If not, I think we can continue with Bobby Antonio from Oxford.
Hi, so yeah, my name's Bobby. I'm working in Oxford with Christian and Hannah on this the problem of trying to use machine learning to improve ocean spin-up. So I'll just tell you what that means. So many of you will know that ocean spin-ups are a bit of a problem with climate simulations because it takes a long time. So it takes about thousands of years for the deep ocean in particular to reach some kind of reasonable state. And obviously, if we have a better spin up, then our climate simulations have better initial conditions. So we really want to make sure we've got a really good spun up ocean. And so also, many of you will be aware there's lots of machine learning emulators of the atmosphere out there at the moment. So, and they're very fast compared to physical models. So we're interested in seeing if we can use those to help improve ocean spin up. And as a side note, it's also interesting to just see how do we couple the machine learning model to a physics-based ocean, because especially as a lot of groups are starting to push these emulators out to more kind of climate time scales where interactions with the ocean obviously become much more important. So yeah, so our proposal is we use GraphCast DeepMind, DeepMind's GraphCast, sorry. The reason we use that is because it provides all the right variables we need to give, well, most of the variables we need to give to NEMO to do coupling, and it's also very fast. So our proposal is just to use GraphCast as the atmosphere and NEMO as the ocean, and we do some kind of coupling between the two where NEMO passes some sea surface temperature to GraphCast, and we pass some things like temperature, humidity, temperature and precipitation and wind into NEMO. So there's a few challenges here that we need to address. Obviously, GraphCast is only trained to work at 2-week timescales, so we have to first of all figure out if there's actually any seasonal behavior in GraphCast, but also these models are known to be kind of unstable, much beyond this 2-week lead time. So we need to kind of address that as well. So I'll just starting with the unstable thing about how stable GraphCast is. So what we've done here is just take GraphCast and initialize it at several different times of the year for lots of different years. So, the top left is starting in January, top right is February. So we've got 2 winter starts there, and the bottom 2 are July and August. So you can see that after about 20 days, GraphCast is clearly producing pretty unphysical values. So the blue here is just the ERA 5 over the kind of 5 years before. This is the Northern Hemisphere only, just so we can see if there's any seasonal behavior. So it's unstable, but we can also see there's perhaps some seasonal behavior going on there, especially you can see in the kind of summer months, it's following the line, the seasonal line well, even though before it deviates. So our approach to making GraphCast run for longer times than 2 weeks is using an analog method. So we take GraphCast and we run it for an amount of time where it's stable. And then at the point, or before the point where it's going to become unstable, we look up in the history of ERA 5, what was the closest state to what we've currently arrived at. And we're currently just doing that based on 2-minute temperature. So we do that, we look up in some kind of way, like, this could be a machine learning model. In our case, we're using something a bit simpler for various reasons. But you look up in some kind of small space, compare that to ERA 5 history, and then reinitialize with that. And that guarantees at least that you're not going to go outside the range of ERA 5. Obviously, there's downsides to that, and you ideally would need a lot of ERA 5 data sitting around in order to reinitialize. Luckily for us, Weatherbench provide all of ERA 5 in the cloud. So we don't actually need to store it ourselves, we just need to pull it down when we need it. So that's good. And obviously, there's going to be some kind of discontinuities because there's never going to be a perfect match with this analog method. But we're hoping that this will still give us a good climatological signal to NEMO, because that's what we really need. We just need it to give it the right kind of signal to get it to a nice spun up state. And obviously, yeah, we don't, so I'll just, our results at the moment seem to show it's pretty good. I mean, so this red is just GraphCast running for a year. So obviously after it's obviously stable because by construction it's been reinitialized with ERA 5, but it's also following the seasonal behavior even at higher altitudes. So we're only matching on 2-minute temperature, but it's still doing well at, say, geopotential at 500. It's still kind of managing to produce a reasonable state there. We did experiment with using more complicated models, like things like variational autoencoders. The problem with those is that when you're training on ERA 5 and then applying it to GraphCast, the distributions of those two data sets are different enough that the variational autoencoder can't transfer to GraphCast. So without generating a whole load of GraphCast data to train on, we can't really use those kind of methods. But PCA is nice in that it's actually transferable from ERA5 to the GraphCast data. So that's what we're sticking at the moment. The next challenge is the coupling. So this is something I've just been tackling fairly recently. So for those of you who know GraphCast, it doesn't actually accept sea surface temperature or any sea surface variables as an input. So that's potentially quite challenging. So we have a few options of how we can kind of make GraphCasts coupled to the ocean. We could obviously just retrain the model. And that's obviously very difficult because we don't have the resources that DeepMind have. We don't have petabytes of storage and hundreds of GPUs to train on. We could just retrain surface variables. So we could say, let's train a model that only predicts 2-meter temperature very accurately based on sea surface temperatures. So that, I mean, that's definitely a viable option. I guess one problem is that we've heard anecdotally from, say, the group at ECNWF, that when they have tried to train machine learning models, including sea surface temperatures, often the sea surface temperatures are ignored because often they're training these models at very short lead times. So there's kind of no guarantee that even if we give it the SST information, it will actually use it. And also, I guess there's a risk that if we come up with quite a simple model to produce 2-meter temperature, we may just end up decreasing the quality of the 2-meter temperature and surface predictions that GraphCast is making. So the third option we have is a physics-based approach. So this has its, obviously, it can be quite challenging as well, but at least it's interpretable. And it also means that when we're when we're nudging GraphCast state based on the ocean, we can provide the same nudges, the complementary nudges to NEMO at the same time. So there's a kind of consistency between how the ocean and the atmosphere are changing, which obviously is desirable if we want to have a nice coupled system. So yeah, so we are currently going with this third approach, a physics-based approach, and I've just got a little diagram here of what our thinking is. So yeah, what I'm showing here is you've got NEMO in the bottom here, and you have GraphCast just above it, and you have something in between them which is calculating the fluxes going from ocean to atmosphere. And we are currently using this thing called ERIE flux code, which is actually a replica of what NEMO already does to calculate its fluxes. And in order to, so it's kind of straightforward to make NEMO update because that's how it's built. You give it some fluxes, it will update its state. With GraphCast, it's a bit more challenging because it doesn't have model levels, obviously, and doesn't have even equations of how temperature and things vary. So if this was a physical model, we could just put these fluxes into the bottom of the model and add those fluxes to the updates of the kind of surface variables. Yeah, with GraphCast we don't have that. So what we're doing is we're assuming a very simple boundary layer model. So I think there's at the boundary layer you have some kind of turbulent mixing, such that you can approximate this as having having constant potential temperature up to the boundary layer, and so if you make those assumptions, you can kind of parameterize how the potential temperature is changing within the boundary layer based on the fluxes at the surface, and so we're kind of using that kind of very simple parameterization scheme as a way to update GraphCast. And what we're kind of assuming here is that these equations are just meant to show that GraphCast is having some kind of change over time, but we're kind of assuming that GraphCast's change doesn't include any changes that would have been due to the ocean state. So we add to that any a change due to the ocean state as well, and the same for humidity and winds. And we also have we'd have a wind stress term here. So yeah, so far we've implemented this at least for temperature anyway, for sensible heat flux. And tried running out GraphCast again, and so far it looks promising. When you run this with when you run this again, you get different matches when you reinitialize compared to not nudging. So that's a good sign that the coupling is changing the trajectory that GraphCast would be taking. So the next challenge is to get GraphCast and NEMO actually running together. There's a couple of challenges like based on the fact that we have to run GraphCast on GPUs and Nemo on CPUs, and not many clusters are built for people to use in that way. And we also got to just do some engineering work on how to make sure these models are running in sync and passing variables to each other in the right way. And once we've got that working, fingers crossed that'll be soon, we're going to run an experiment where we initialize the system with something like a strong El Nino year or a weak El Nino year, and see just how the behavior changes. So that's it. This is the funding slide.
Thank you a lot. So are there questions to Bobby's talk? If not, I'd had one. I was wondering, when you showed this kind of annual cycle, it always looked like GraphCast was running a little shifted to that one. So a little later than ERA 5, especially in the first one. So is that possible that it comes from drifting, kind of that the season is slightly shifted? Or do you have, especially the first and the last one, when you see it increasing, it's always first ERA 5 and GraphCast comes a little later, or are there other reasons for that? Does it come from?
Yeah, so I think I would attribute this kind of thing to the fact that when you're obviously when you use an analog method, you're initializing from 1979 up to 2019. And here we're actually testing on, I believe this is 2016. So, you know, the matches it might get, you know, in general are from a year much previous to what we're kind of testing on. So I can imagine that would mean, you know, when there's some behavior that's kind of typical of now, and we're sampling from a different period, maybe a few decades ago, there could be some kind of shifting. But I don't know. I mean, it could also be that I just haven't sampled enough ERA 5 to really get a sense of the real spread of ERA 5, and it might well be within the variability of ERA 5 anyway.
Okay, thanks. Are there more questions? I don't see any, so I guess we continue with the presentation from Gunnar Behrens.
So, hi, my name is Gunnar. I'm a member of the University Bremen group, and here in that presentation I will quickly go over the work that I did about stochastic and multi-member deep learning parameterizations for convective processes here. And so my talk is basically has a few parts. So first of all, I will quickly moderate to the topic of stochastic parameterizations and also multi-member parameterizations. Then I will quickly explain the Earth system modeling framework that I'm using and the superparameterization. Part 3 is then basically how could we construct stochastic and multi-member parameterizations. And in part 4, we will have a look then on these uncertainties that we get if we test or if we evaluate them against test data from an Earth system model or from hybrid simulations. And in the end, there will be a brief summary and outlook. So simply let's start. Suppose you have some sort of deep learning ensemble. So a set of different neural networks, for example. So the first step is basically to have a look on uncertainty quantification in test data. So basically reducing the biases of this uncertainty quantification. And one way is with a probability integral transform diagram. What you do is basically you rank your true observation inside the ensemble. That's kind of the x-axis, so the rank of your true value, and the y-axis gives you the probability associated with that rank. And what you usually see in the beginning is either an underdispersion, so that that your somebody is not muted, but anyway, so what you see is basically that your ensemble is underestimating the spread of the true value, or the opposite case, an over dispersion, so where the spread is overestimated. And ideally we want to have kind of this green line in the end. And if we achieve that for a multivariate data set, then the next step is basically then to couple it to the system model, perform some hybrid simulations, and also try to interpret these uncertainty estimates that we're getting based on these hybrid simulations then. And this brings me now to the Earth System Modeling Framework and that we're using. Here in that case, it's the Community Earth System Model version 2. And it has a really coarse resolution of 160 kilometer each grid cell. And you know that on 160 kilometer, you cannot directly simulate, for example, convective processes, as it's shown here. So one way to go forward is basically to nest high resolution grid columns in each large grid cell. They have a typical resolution of 4 kilometers, and that's called SP or superparameterization in that case. And how is this superparameterization working? So basically, the superparameterization gets some sort of thermodynamic, large-scale variables, so the theoretical temperature profile, and the SP with its own numerical cores, it computes then subgrid processes. So for example, convection, turbulence, and also radiation with respect to convection. And then you could update the large scale state based on these tendencies that you're getting from the superparameterization in the end. And in our work, we mirrored that approach and build a stochastic and multi-member parameterization with similar input and output pairs. Regarding the inputs, as I said, we oriented ourselves on large-scale CAM variables. So for example, here specific humidity profiles. But additionally, we also added the precipitation from the previous time step as a source of a memory term of our networks, because we found out in the beginning that it strongly improves the reproduction skill of, for example, surface specific humidity tendencies and also the radiative fluxes that we need to couple to the land model. And regarding output terms, as I said, we have a lot of tendency terms, so specific humidity tendency profile, for example, some precipitation rates, so snow and precipitation rate, and then these radiative fluxes that we need to couple to the land model at the current stage, or at the later stage then also to the ocean model here. And one way to construct the stochastic parameterization is simply by use a deep neural network and add one dropout layer to that network. And this dropout layer is then basically randomly clipping some connections in that network. And if you repeat then, predicting with that network, then you get a stochastic parameterization. And here in our case, that's DNN dropout. That's the first approach. The second approach is a multi-member approach. So, and here basically we have different neural networks with varying hyperparameters, so batch size, learning rates, whatsoever. We tested two different network types, one with deep neural networks and the other with variation encoder-decoder structures. And if we, without random averaging, so without changing the members in space and time we are averaging over, we're getting deterministic parameterizations, and that's DNN overbar or VED overbar. And if we additionally apply random averaging in space and in time, then we build stochastic parameterizations. And one example here is DNN ensemble. And the third approach is again only focusing on one single network, and here we use a VED. And in that VED, we perturb the latent space, so this latent variable set here with Gaussian noise. Either you can choose Gaussian noise that has a constant or has a constant magnitude along all latent dimensions, that's VED static with isotropic noise, or the opposite case with varying magnitudes, that's the anisotropic case, and this is then VED varying. In both cases, we are building stochastic parameterizations. And now let's basically start simple. So focusing now on the uncertainties itself. And with these stochastic and multi-member parameterizations, they enable us to basically evaluate also these uncertainty quantifications that we're getting with these parameterizations, especially from convective processes. And we use different metrics. So for example, spread skill diagrams, probability integral transform diagrams, and also the continuous rank probability score. And what you see here on the right side is basically one example for specific humidity tendency at the surface. Again, the x-axis shows you the rank of the test data set within the ensemble, and the y-axis gives you the probability associated with that. And the color coding is basically showing you the different parameterizations we implemented. And here the ideal case is highlighted by this gray dashed line. And if we conclude over all the different metrics that we are having a look on, then we see that in almost all cases, we get the best performance with DNN overbar, as it's seen here in that line, because it's very close to the ideal case, and also with DNN ensemble, but not here for probability integral transforms due to this random averaging. Then afterwards, we see also that the latent space perturbation is also good to calibrate these uncertainties overall, but we see that we're getting a strong reduction in deterministic skill in the end. And having that now, then it's not surprising that we tested our approach, coupling first of all DNN overbar and DNN ensemble to the community Earth system model. And we conducted runs that were stable over 5 months. They crashed in month 6 in a partly coupled case. And that means that we basically couple all variables except for the cloud ice and cloud liquid water tendency fields, because they were really, really problematic in our case. And now we could also have a look on how these uncertainties are looking like in these hybrid simulations. And here I basically show you 2 examples here. So for February 2013 conditions for DNN overbar, in the upper plot, you see the temperature tendency in the upper planetary boundary layer. In lower plot, the snow rate. And plotted here is basically the interquartile range, so between the 75th and the 25th percentile here in that case. And what you can show here is basically that the parameterization here in that case gives you automatically, or you can see an influence on some drivers of convective convective processes here in that case. So we see, for example, elevated interquartile ranges associated with topography. So for example, here the Himalaya or the Rockies here for snow precipitation rate, and here near East Greenland. And also we see a strong influence of the convective processes, so along the ITZZ or on other levels for the mid-latitude storm tracks. And moreover, what was most surprising for me, and I may have to shift that because you cannot see it, that you see also a bit of influence coming from the ocean. So here you see this elevated uncertainties with respect to the ocean currents. So in that case, the North Atlantic current or the Gulf Stream. I know that was quite funny. So to conclude, basically, our multi-member parameterizations, they allow physically interpretable uncertainty quantification. And we see also that there are some characteristics of the general circulation that we could connect to these uncertainties there, which is surprising. And now to summary, as I said, we were able to calibrate uncertainty quantification in the multivariate test data set. So with deep learning here, both based on test data and also in hybrid simulations. And then we see also that our deep learning stochastic and multi-member parameterizations, they reduce some precipitation biases in Earth system model simulations compared to traditional convection schemes. So for example, the diurnal cycle is improved here. And Outlook, what I will do next is basically translate that approach from SGCSM to ICANN. Then at a similar stage, evaluate how these stochastic convection parameterization is then, whether these uncertainty quantification is then meaningful based on some high resolution data. And then finally is also kind of the aim to improve and also better understand air-sea interactions over the Southern Ocean. So basically connect my work and also the work previously from Jan there together. And with that, I thank you very much for your attention. And I'm ready for questions. And here's the funding slide again.
Thank you a lot, Gunnar. So are there any questions? Hannah has a question.
Hi, thanks. Thanks for the talk. Just checking, did you try coupling the autoencoder decoder one in as well?
No, we did not. We did not try that because our Fortran Keras coupler is a little bit, little bit tricky to handle, and the only thing that we tested were deep neural networks due to the fact that we know that the coupler was working for it. So it would have been additional work to try that with a variation encoder decoder, but it's a great question, and I will explore that also in my further work then with ICANN data.
Yeah, because the encoder decoder setup feels like a really nice way of doing it, doesn't it? And I was also really interested.
Absolutely.
Yeah, I was interested. It looked like it was over dispersive. Is that right from your offline testing then?
In this offline testing, let's go back. So it was. I mean, kind of. That's basically again kind of a set of different variation encoder decoders where you see this. Here there's over dispersion. Yeah, it was over dispersive with respect to the surface specific humidity tendencies, but for levels above, you can see that these curves were nicely matched, kind of the ideal case. So I computed also, I think at some point, the probability integral transform distance. So basically kind of the area between these things. And there you saw that the VADs, so with Gaussian offset, they were the best for that metric, but not obviously for the surface values, where we have kind of a bit of overshooting.
Mm-hmm. Yeah, thank you.
Any more questions? Else, I should also notify you that the next Storms, Eddy and Science seminar is on the 16th of December, again at 2 Central European time, or 1 hour different for Oxford. And yeah, that's with talks about Southern Annual Mode by Ting Cheng, influence of winter atmospheric circulation on fast and future Antarctic sea ice loss by Daniel Topal, and the fate of fresh water around the coast of Greenland with Fraser Goldworth. Okay, then thanks all for coming, and yeah, see you in the next EERIE meetings.